Hi, this is Dr. Vev. In this video, I'd like to talk about how to determine relative and absolute errors or uncertainty. Let's suppose you have a coin that you wish to buy, and let's suppose it's marketed on eBay as a gold coin. You want to make sure that you're getting a gold coin and not some fake item. So you ask the seller to take some measurements. Well, the seller uses whatever crude devices at their disposal and gives you these measurements. The thickness is 4 millimeters with an uncertainty of 1 millimeter. The diameter is 5 centimeters with an uncertainty of 0.1 centimeters, and the mass is 100 grams with an uncertainty of 2 grams. So first of all, to be precise, I should write this as 5.0. Okay, now how do you decide if this coin is gold or not, and if you want to make the investment? Well, there are several methods to go about it. Well, let's first of all find the average density. To find the average density, there's just one method, and that's simply got by the definition of density. So the density of an object is just equal to the mass divided by its volume. The mass is given, but the volume is not. A coin looks like a cylinder, so the volume of a coin can be found by simply multiplying the area of a circle by the thickness. The area of a circle is pi r squared, but since diameter is given, you can write it as pi d squared upon 4. Because radius is diameter upon 2, and when you square it, you get d squared upon 4 times the thickness. So that's the volume, and so from this we can get the density rho. Density is equal to, when I divide this by v, I'm going to get 4 over pi, and then m over d squared t. The average value of the density can be computed by simply ignoring the uncertainties for each of these measurements. So let's figure that out first. It's 4 over pi. That's going to be 100. The units are going to be grams per centimeter cubed. So I'll write that at the end. That's 5 squared. And the thickness is 4 millimeters, so be careful to convert it to centimeters first. And then I have grams per cubic centimeter, which I'll write as cc. Now if I use a calculator, I can figure this out. The answer is 12.73 grams per cc. So far, not promising. If this is the average value, then it's very unlikely to be gold, because the density of gold, for reference, rho gold is about 19 grams per cc. So if this were something like 17, then you could possibly expect it to be gold, but it's unlikely to be gold. Well, it still could be some impure form of gold, so we have to put some error bars on it. There are two basic methods. One is called the absolute error method, and it's not very precise, and you should use this only if you're not able to do the problem any other way. So I would call it a poor man's method of finding errors, but it's still worth learning, because there are problems where errors are difficult to find any other way. So the absolute error method proceeds by finding the absolute error directly without finding the relative error first. There are two ways to do this. The absolute error, delta rho, is rho max minus the average value, rho bar, or you can think of it as rho bar minus rho min. Each of these will give you a different value, so I'll call it delta rho 1 and delta rho 2. Let's figure this out. What would I get for each of these absolute errors? So first of all, what is rho max? Rho max is what you get if you put the maximum value for each of these things. So that's going to be 4 over pi. In the numerator, instead of putting 100, I'm going to put 100 plus 2, 102. Rho max, the maximum value of rho, is got by minimizing the denominator. So I'm going to put 5 minus 0.1, or 4.9 squared. And then I further minimize t. Minimizing t means that you subtract. So this is going to be 0.3 instead of 0.4. There's no square. I'm sorry. I didn't mean to write the square there. So this grams per cc, when you evaluate this, and I've done this off the screen in my calculator, I get 18.03. And that makes sense. It is bigger than the average density. In the same fashion, let's try to figure out what rho min is. I just want to show you something interesting. Rho min is got by putting quantities to make this as small as possible. Well, that's done by making the numerator as small as possible. 100 minus 2 will do it for the numerator. And the denominator as big as possible. Well, the denominator can be made as big as possible by writing this as 5.1 instead of 5, squaring it. And then for the thickness, instead of 0.4, I'm going to write 0.5. Remember that this point is there because I'm going from millimeters to centimeters here. Grams per cc. And off the screen, I've worked this out also on the calculator. It turns out to be, this turns out to be 9.59. Let me underline a few of these results. So you can see that the maximum value and the minimum value are where they need to be. So let's find out delta rho 1. Delta rho 1 is got by taking the maximum value and subtracting the average value from it. So I'm going to give you that result now. Delta rho 1 is 18.03 minus 12.73, and that's going to be 5.3 grams per cc. Now 5.3 is pretty big uncertainty, but notice that 12.73 plus 5.3 still puts you under the density of gold. So even with this crude method, you know you're not looking at a pure gold coin. Let's find out what delta rho 2 is. That's the method of subtracting the minimum value from the average value. So the average value is 12.73, and if I subtract the minimum value from it, I get 3.14. Not sure if that is correct. I thought, yeah, I think it is correct. 3.14 grams per cc. So you can see immediately that this gives you a better value than that. So which do you trust? There's no real way to think about that. You can take the average of these two if you wish, and find the average. The average value of these two is the same as taking another formula, which I'll call delta rho 3, and that's going to be rho max minus rho min divided by 2. You can observe that doing rho max minus rho min and dividing by 2 gives you the same result as averaging these two, because when I take rho max minus delta rho, and then rho minus delta min, and I subtract these two, that's pretty much going to be the, if I add these two, these two values and divide by 2, then I'm going to get the same thing. So this is the same as delta rho 1 plus delta rho 2 divided by 2. So that's these are the crude ways of doing this problem. The more refined way of doing this problem is by using what's called the relative uncertainty method, and if it's possible for you to do this, you should always use it. The relative uncertainty method is a very good method because it takes us very close to the true method, which is a second order uncertainty method, which I'll also talk about. So the relative uncertainty method, you can start by writing the formula for density slightly differently. You write it as powers 4 over pi m to the power 1 d to the power minus 2 t to the power minus 1. So that formula there, you can write like that. The formula for relative uncertainty can be used, and that formula is the fractional change in the density, that is the change in the error in the density divided by the average density, is given by the absolute value of the powers to which each of these factors is raised. So that's delta m over m plus absolute value of negative 2 delta d over d plus the absolute value of negative 1 delta t over t. So you can get this very quickly because delta m is just 2 and m is just 100. The units cancel out, so I won't write them. This is 2 times, because absolute value of negative 2 is just positive 2, 0.1 divided by 5, and lastly 1 over 4. The reason I like this method a lot is because you can immediately see which are the big sources of error and which are the not so big sources of error. So you can see that the thickness is the worst measurement because it contributes 25%. This is also sometimes called the percentage error. So each one of these things is a percentage. There's only 4% uncertainty coming from the diameter measurement and only 2% uncertainty coming from the mass measurement. The total of all these is 0.31. And once I have delta rho by rho average, I can find delta rho by simply multiplying rho average on both sides. Well, rho average is just 12.73 grams per cc. So if I multiply that with 0.31, then I get 3.95 grams per cc. So this is by far the most refined calculation. It comes close to the delta rho 2 there. The absolute gold standard, if you wish, for error analysis is what's called the second error. So the second order error, this is sometimes called the first order error. The first order error is always bigger than the second order error. So the second order error is used generally for normal distributions. In our experiments, we're never going to have as many data points as we need for normal distributions. I think the second order error is a little bit of an overkill for this course, but nevertheless, you need to know what it is. It's actually really simple. It's whatever you had in the first order error, you put inside the square root and square each term. That's all it is. Now if you square each term, you don't have to worry about the negative sign. Alright, you do that, and then you substitute all the values in and calculate delta rho. You're going to get delta rho is 3.23 grams per cc. So you can see that each of these methods gives you a completely different uncertainty, and which one you trust is really a question of how many data points you have and how good of an experiment you're running.